Hello, everyone. I couldn't have a better start than a tricky question, so thanks for that. And hopefully, by the end of these 10 minutes, everyone will get an answer. But we're gonna be at the booth, and we're gonna take questions after as well. Let me just get started. I have a lovely picture. I think we've seen enough messy cables and setups. Let's abstract a bit away and look at the future. This is like how we envision fault-tolerant quantum computer in operation. Is a quite generic scheme if you want. It takes you start from the user, the application. Now you're talking about logical qubits and logical operations. You have different phases, if you want, of compilation, transpilation, until you get to our, well-known physical layer type of implementation and circuit. There is calibration in the loop. There is all the elements have been discussed today. This information gets propagated to the control system, and it gets propagated to the quantum error correction stack. Can be generalized, obviously, to any provider. So you will see we're going to focus on Riverlane, but it's a generic solution. Then the control system performs the physical operations, return the measurements. Measurements are discriminated, return to the quantum error correction stack, and at that layer, the decoding happens. The decoding takes the encoded information that have been generated with the circuit, understands whether there was what type of error has been affecting the qubits, proposes a solution, and returns back to the control system with the proposed solution. Now, let's focus on us, Riverlane, the system in the green. In the green boxes, we have obviously something real that you can see at the booth as well. Let's start with what are the two challenges that everyone that is building this type of solution is facing. The first one is the backlog problem. And this is partially the answer to the question was raised before, what you want to be able to achieve with regards to error correction is to be able to receive and compute and decode continuously a stream of measurements, and avoid generating, if you want, a backlog, so accumulating them and not being able to keep up with the production of the values. Classical problem applies in quantum. What it means is if you are not fast enough, and I will show you some numbers, you're not doing any computation at all. Second problem is less of a blocker, but still is quite annoying. When you go outside the Clifford gates and you implement not Clifford gates, and in this example, everyone talks about T gates, and you have the problem that your response time, so that the time it takes for you to make a decision, propagate it back to the control system, becomes, if you want, a series of knobs, of logical knobs in your system that are affecting the overall clock rate or logical clock rate of the system, slowing down pretty much everything. Now, some numbers. Now, obviously, these are relatively anonymized, generic numbers. We expect them for some of them to actually decrease, as in particular or increase. In particular, response time and throughput for AMO are supposed to get the throughput to increase and the response time to get shorter. And how do you read them? So the decode throughput is really being able to process. You can reverse it if you want in microseconds or nanoseconds, and that's the frequency of your measurement cycle. The decode response time is errors happen in space and time, so you can't just correct looking at the space. You need to look at the time dimension. That means that you need to perform multiple rounds of error correction, of syndrome extraction, and do error correction on that. It means you create, if you want, a pile of them, and then you make a decision. So that's why the response time is affected by accumulating, if you want, these errors, and then sending back a decision. Now, what are the, if you want, the requirements before we jump into an architecture? They're quite straightforward, I think, and all the talks today were addressing some of them. If you want, we need a distributed control system that can scale, so enough qubits in terms of control and readout. We need to have a way to route the information of the measurement and tell also where they're coming from, not just send them as if you want, a labeled data. Operations that this measurement then needs to become the input for the decoder, that is a syndrome. And finally, this we need to be able to perform if you want, the conversion and the decision on them on the flight. Finally, in some circumstances, like when we're performing a logical T-gate, we need to propose back a correction to the control system, and the control system needs to be able to perform it. I think we spent enough time as Riverlane on these topics. Sorry for bombarding you in this session. Lots of questions on QCI. I think that went well. Syndrome, as I said, is the process of getting the measurements and converting them in inputs for the decoder. And observable was presented before as the encoder quantity information. How does it work architectural-wise? So pretty much you can see it as a pipeline. You have a control system that is implementing a QCI. In our case, if you're talking to us, a QCI interface. There is a QCI file, so a physical layer that sends the data. Data are obviously packed and encoded. Transmission over an optical cable. The FPGA that we have in our boot transceivers have about 25 nanoseconds latency on the file level, so they're quite performant. Then you enter in the pure digital domain, and there is the pre-processing for the decoder, the decoding itself, and the results that are returned over QCI file back to the system. Now, all of this has interesting elements to consider. Time-wise, as I was saying, we want to guarantee both the response time and the backlog, and be within the backlog. So all of this, every time you see a watch, a clock on the screen, we have to stay within the hard real-time constraint that is specific to the quantum technology. Now, this applies, as I said, to all the steps. So even getting the data in requires fast processing. My colleague Annick presented gave you a bigger overview of this, and this was the question on how to implement it. This is what we provide our partners and users. This is implemented it's provided as RTL, so can be integrated. Then internally to our system, it is obviously specific to what we need to do. These data are converted into memory transactions that are then that can be passed to the next stage. Is important because this is requires we can have multiple inputs. We can have out of order packets. The control systems are generic and all different, so we need to be able to cater for different type of configurations. Finally, after pre-processing the data, the syndrome itself needs to be fed into the decoder or in the decoders, and they need and the decision on what if there was a logical error in the current route needs to be propagated back, and all of this needs to be continuous. Obviously, there is an element of configuration as well that goes along with the runtime, and we need to fine balance the two so that we are never blocked during configuration. Finally, the reverse. We are going out of our system and back to the control system with the response. As before, we're trying to be as lightweight, as fast as possible. We need to cater for synchronization and for also the fact that the control system and the QC stack need to operate at different clock domains at with different periodicity and if you want in two different environments. short summary if you want. First thing is a full tolerant quantum computer really requires a QEC stack. You have without quantum regression, we are not really able to produce the computation that we need, and we need to be experiments ready. A presentation before from Samin was explaining all the steps that are required to get if you want the computation, and the user's happy with that. I wish we had more figures on latency and overall budget. We can give you answer, but we don't have like a full table, a full plot to show you. They are. I wouldn't say they're coming next APS. We're trying to make them coming sooner, but that's where we are today. Just to say, come and see us at the booth. We are also hiring, so the usual. Please, US and UK, and if anyone. Thank you.
Just a question, and kind of related to latency, but I was just curious, like, why are you using a 12.8 gigabit link? You can obviously use faster links, right? Like, there are faster IPs, and are you limited by your processing speed, or is it the link speed? Just curious if you can comment on that.
Yeah, is a good number, as in the bandwidth that we need is, we estimated the bandwidth that we need. The way we did it was we expect 1,000 qubits to be covered by one system, by one link. Then we said we are strong on, I don't know if you've seen our work on soft information, but that allows us to increases, if you want, the number of bits per measurement to up to 8 bits. So we made it 8 gigabit a second if you want. And then we round it up to a frequency that was like sustainable by most of the FPGAs on the market. We could have done 25, but some of the legacy technologies will not get there. So it's really the transceivers that are.
No, but because the transceivers are faster, right? Like
no, not all of them. The GT.
Like, I'm sure like there are a lot of IP solutions they use in data centers are like even of the orders of hundreds of gigabits per second. They
aggregate multiple channels. Not every control system has that type of. Some control systems have been around for 5 or more years, and they have GTX transceivers that are stopping at 12.5 or even less. So it is a I mean, the future will be, in the future they will keep pushing up, and we can then double rate.
Okay.
Easy enough. It's not.
Thank you.